Hello, everybody. We're talking about the 1932 Nobel Prize in Physics, doing a little bit different format here because a couple of things. Number one, I wanted to tell everybody there was no 1931 Nobel Prize in Physics. The committee determined that nothing that year met the criteria. So they skipped it and put the prize money back into the general fund and waited till the next year. This year, 1932 ushers in a whole new era of not only physics, but these prizes. And I felt doing these things a little bit differently might help because they get a little more complicated from here. This year, 1932, the prize went to Werner Heisenberg. Now, this one went to him for the creation of quantum mechanics, the application of which has inter alia led to the discovery of the allotropic forms of hydrogen. But there's a whole lot more to this guy than that. And that's why we're going to do this new format, because he has a whole history that I think is important, because I think as we go into this era, we are entering the World War II time period, and which you could really kind of call the first war of physics in a weird kind of way. But we'll get to that. But I think starting in this new format, we're going to take a little bit longer per award winner. And go into a little bit more detail about not only what they won the prize for, but what they did after that, because it starts to become very important. So let's get into Heisenberg. No, not that guy, the other Heisenberg. Yeah, that's the Heisenberg we're looking for right there. So before this time, a lot of people were circling around quantum mechanics, and they were starting to put together the pieces that would ultimately become the overall theory. They were pulling in wave particle duality, the electron, a lot of that other stuff was starting to come together. But in this particular case, the work that Heisenberg did, he had to take Niels Bohr's theory of the atom, in which the electron absorbs and emits radiation in fixed wavelengths when jumping between fixed orbits around the nucleus. Remember, we talked about that energy level. It can only go up in integer multiples. It can't go up a half an energy level. It has to go up 1 or 2 or 3. Now, that theory provided a great description of the spectrum created by hydrogen atoms, but it needed to be further developed to suit far more complex atoms and molecules. And I even mentioned that when we talked about Niels Bohr in his Nobel Prize. Now, in 1925, Werner Heisenberg came along and formulated a type of quantum mechanics based on matrices. And in 1927, he proposed his sort of famous uncertainty relation, which sets limits for how precisely the position and velocity of a particle can be known simultaneously, which is the sort of ubiquitous Heisenberg thing that we all talk about from time to time. So let's go figure out what the heck that thing is. So usually I try to stick away from the math, but this time the math actually matters. So the Heisenberg uncertainty principle is what everybody's always talking about with this guy, among other things. We'll get to that other stuff in a minute. And what the uncertainty principle tells us is that there's an inherent change that you impart on a system just by taking a measurement, just the mere act of measuring a variable of a particle. So it's commonly applied to both position and momentum. And all this means is the change in x, that delta there, the Greek letter delta, that just means change. X is position, P is momentum. So if you multiply the change in position times the change in momentum, which is, how fast something's moving, it involves velocity and mass and all that stuff. It's always greater than or equal to some constant. H is just Planck's constant, 4 pi is just 4 pi. So when you've got this uncertainty, the more you know one of those, the less you're going to know the other. Now, why the heck is that? That just seems counterintuitive, right? We can know what kind of momentum it has, or we can know where it is. We can't know both. Well, the moment I go take a measurement, I've caused a change, because these are particles. They have charge, except the neutron. But when you try to take a measurement on a point particle, you're going to impart some energy into that particle, and it's energy it didn't already have. So if I go say, hey, I'm going to go take a measurement of you, and you're an electron, and I do that with some other measurement device that happens to involve bouncing a photon or bouncing another electron, or some other means of taking a measurement by using an electric field or something else, what I'm doing is I'm changing the momentum of that particle, so I'm not going to know its position anymore. So I can either know the position or I can know the momentum, but I can't know both very well at any point in time, because the mere act of taking that measurement imparts additional energy into that system, and that additional energy is going to cause a change in one of these two things. Now, sorry that is that way, the way it is, but this thing seems to hold, and it's held for all kinds of situations in the quantum realm. It used to drive folks like Einstein crazy, but it seems to work, and all these years later we're still using it. So the Heisenberg uncertainty principle is absolutely there, and it has absolutely nothing to do with people using RVs for nefarious activities, but it is a tried and true part of our quantum mechanics world. And it's one of the many things Heisenberg did to really kind of solidify the quantum world for us, and bring it into the state we have it in today. And he did a lot more than that. So let's get to that other stuff, because he was an important person in the world of physics, because at this point there was starting to be a ramp up to World War II. We were in between the two world wars, and people were kind of picking sides, and eventually we're going to start to be off to the races, where a lot of physicists are doing a lot of work, and we need to kind of be aware of who was on which team. So let's take a look. Now, during World War II, and Heisenberg was actually born in 1901. He didn't pass away till 1976, but he was, a great theoretical physicist. He did work in the quantum world. And during World War II, he was actually a main contributor to the German atomic program, which was in direct competition with the Manhattan Project to try to develop nuclear weapons out of this type of technology. In fact, in 1941, he even visited with Niels Bohr in Copenhagen to discuss his nuclear research. And when Oppenheimer here in the United States formed the Manhattan Project and had that going, they were in direct competition with the group that was at least partly comprised of Heisenberg. And he was one of the people who really did have a great handle on that theoretical side. So, there is a lot of questioning now in modern times. This is 2024 of, well, were we really justified in having the Manhattan Project? Well, yeah, depending on how the war went in Europe, that they were going to have that bomb, and whether or not we had it was secondary to that. So, whether or not that project was necessary or not, that's for historians to figure out. But it is worth pointing out that the German program did have Heisenberg on their side. Now, after the war, he did other things. He was not thought of to be a large danger as some of the members of the Nazi Party were, but he was involved in their nuclear program. Now, after the war, 9 of the scientists who were very prominent in the German nuclear program, who had published papers and other things, were captured by Operation Alsos and incarcerated in England for a while. 10 of those scientists, including Heisenberg, were held at Farm Hall in England. It had been this sort of safe house. They were interrogating them all out, and the transcripts reveal that Heisenberg, along with other physicists that were kept there, including Otto Hahn, Carl Friedrich von Weizsäcker, and we're kind of glad that the Allies actually won World War II. Heisenberg told other scientists that he'd actually never contemplated a bomb, and only an atomic pile to produce energy, which I showed you in the other picture. When the Allies took over that atomic pile, they were using it as research to kind of try to figure out how to generate electricity. Now, whether or not that was the extent of their interest is still, up for debate. Not something I'm going to go solve, but he was certainly adept in the nuclear world. But at that time, with those prisoners, the morality of creating a bomb for the Nazis was discussed. And a few of the scientists expressed genuine horror at the prospect of nuclear weapons at all. And Heisenberg himself was very cautious at discussing nuclear weapons in general. So, what really went on during World War II, that's one for history books. But he was around in the world of physics until 1976, which was actually within my lifetime. I was born in 72, so he was alive when I was. We're not related, but still. And I'm take that for what it's worth. But he did make contributions to theoretical physics long after the war. And I think at least the world of physics gained for his presence in it. Now, again, the Manhattan Project is a completely different subject matter, and someday I will do videos on that, especially on the science around it, and whether or not the Germans were really close or not. Because I think the movie Oppenheimer by Christopher Nolan captured that story very, very well, at least on the Allies side. But I'm not sure the German side of this that is really all that well known. And there's a lot more to it than what's in the Heisenberg story. And that part of that is actually fairly well known, at least in the scientific community. So I'm going to try to do some work on doing videos so that can be a little bit better known. But I hope everybody's enjoyed this new format I'm doing, and I hope you know a little bit more about Heisenberg and his uncertainty principle now. And I do think the prizes to come are a little bit more modern, and I think we're going to all learn a lot. Now, this particular one, without people like Heisenberg and the uncertainty principle and other things, we wouldn't have learned quantum mechanics, we wouldn't have known the nuclear world as well as we do, and nuclear power wouldn't be an option. That is a double-edged sword, and with any technology, especially in the world of physics and some of the hardcore sciences, biology, all of chemistry, um, we can build a device, we can understand the science, and we can build something to do with it, but how it's used is up to other people. You can always take just about any science or technology and turn it around for nefarious uses. That doesn't absolve people for it, but I'm not trying to say, oh, scientists are innocent. That's not always the case. But I do think that understanding technology and understanding science, it can be used for good things and for bad things. Like nuclear power, for instance, can be used for great things. Nuclear bombs, on the other hand, can be used for horrific things, and it's essentially the same science at the core. So I do hope this video has been interesting to you. Please click subscribe and like. It does help me out with the algorithms, and we'll see you on the next one. Have a great day.